Hello, I'm Robert Baumann from the Dresden University of Technology, and today we're talking about on how to find a correct laser system for your application. So the task is today that you have certain kind of compartment or sample that needs to have a certain surface property, such as in terms of wettability, tribology, coloring, or antibacteria. And we can have a look in the nature that gives us perfect blueprints onto this surface property, such as the rice leaf in terms of wettability, the shark skin for tribology, or peacock feathers in terms of coloring, or any kind of insects that have antibacterial surfaces. And if you have a closer look on those examples, you find that they have some unique microstructures on their surface. And what we could do, or what we want, is to copying those microstructures onto new materials to get those surface properties on new materials. So we have to look in the absorbing of laser radiation. As you can see here, we have a diagram showing the laser wavelength as well as the reflectance on the side. And depending on the material, different kind of material interact different with certain wavelengths. So when we talk about laser surface structuring, most of the time you're using a near-diac laser based on the near-infrared wavelength at 1064 nanometers, as well as the further harmonic, which is 532 or 355 nanometers. And depending on the wavelength that you've been choosing, you're seeing the reflectance or vice versa, the absorbance differs from each other. General rule of thumb, as you could see, most metals absorb strongly in the ultraviolet range of a laser system. The absorption in infrared, so close to 1000 nanometer or 1 micrometer, is generally low. But we also have to consider that sometimes the reflection or absorption is driven by temperature also, which means if the material is getting heated up, that will influence the absorption activities as well. So, for example, if you have a carbon steel, it's so totally sufficient to use an infrared laser system, because here you have an absorption of around about 40% or a reflection of 60%, as well as for aluminum. But if you have, for example, copper materials, I wouldn't recommend to use an infrared laser for that, going more into the green spectra or visible spectra of it, or even the UV one, because here the absorption of those materials is much better and much higher than in the infrared, and higher absorption means also your process is more efficient. And as already mentioned, that some metals you have to make sure you find all those informations in the internet, like copper, as well as if you have silver, for example, they are very high reflecting in the infrared radiation as well, already at the visible spectrum. So you have to go there into the ultraviolet spectrum in order to process those material get a better light material coupling. So the next thing would be to choose what kind of pulse duration you should choose. In surface texturing, we have femtosecond laser, picosecond laser, as well as nanosecond laser for choosing. And depending on which kind of laser source you choose, you get different kind of surface quality at the end. So as you can see here, those SEM images, depending on what kind of pulse duration you're being using, you have any kind of residuals on the surface or any kind of spatter, and this is something that you need to choose about for your own, what is still acceptable for you and your customers, and this will later determine what kind of beam source you're being using. So what is the difference from each pulse duration? For example, if we have a look here on the left-hand side in picture number 8, this determines the classic interaction between photothermal ablation. So we have a short pulse laser system that gets absorbed in our material, and here we have some melt that is generated as well as some vapor, and the vapor is pushing out the melt over a recoil pressure and leave those melt deposits at the edge of our hole, which you could see at the SEM image down below here as well. And furthermore, we have some heat conduction that takes place into our material. That is here, you can see that somehow indicating by those white area in the SEM system. And on the contrary, if you're using ultra short pulse lasers such as pico or femtoseconds, here we don't have such a huge melt pool. We have more like an overheated liquid that gets vaporized pretty quickly. So we have much more vapor or less melt, and therefore we have a minimal thermal influence in that matter, which means that it's a better control for the laser beam processing and gives you a much better processing quality, as you can see at the SEM image on the downhand side here as well. And of course, to choose what kind of pulse duration is just acceptable for your case is that you can calculate it over the linear thermal diffusion length over this little formula here. So here you can calculate the length of how much the material or the heat will conduct into the material. So it depends mostly on the heat conductivity of the material that you want to use, the laser pulse duration. So this is the factor that you could change by choosing different kind of laser sources. And of course, the material density and specific heat capacity is somehow fixed based on the material that you're being used. So the only thing that you will change here is the laser pulse duration, depending if it's nanosecond, femtosecond, or picosecond, and what kind of amount of those seconds. So in general, this is the characteristic that is the distance that describing the diffusion, so the heat conduction into your system. And that in laser processing, mostly this heat conduction leads then to a change in the material and the so-called the heat affected zone, where you have, for example, a grain refinement or the grain structure is changing within that. And that might influence your later on property of your sample. And you need to consider that and calculate that what is still acceptable, what kind of length control there you have. And with this one, you know exactly what kind of pulse duration you use, and further on, what kind of laser source is being used later on in your processing machine. And after that, for me, comes then the most crucial one. Here you see a short diagram. You see on the x-axis I pointed the wavelength, and on the y-axis it's the pulse duration. So based on that, we have starting from nanosecond, picosecond, femtosecond, really as a broad overview. And then from the wavelength, we start from the infrared, going to the visible and then the UV. And what I will draw here is more like the costs that you might have for buying the laser source. So if you choose, you have an infrared wavelength and nanosecond is still enough, then the price for the laser source will be relatively low. And with this, you can see already if you have to go to picosecond or if you have to go to the nanosecond infrared visible spectrum, it will get more and more expensive. So the cheaper it is, the greener it is, and the more it goes into red, the more expensive will be the beam source in that matter. So already seen, so femtosecond visible is getting more and more. So the general rule of thumb is the shorter the wavelength gets and the shorter the pulses get, the more expensive will be the beam source that you will have on your system. So if you can process your sample and your abilities with a nanosecond infrared one, you will have really good cost effectiveness. And as I already mentioned before, that most metals always absorb in the UV spectra, and based on that as well, with femtosecond will improve that even further. So with femtosecond UV, you can make, let's say, the majority of all materials you can process with this beam source. But you have to make sure that this beam source is also the most expensive one in buying that, and you really have to make sure and have to calculate, do you really need this, or if you can make it with a beam source that is much cheaper in order to gain a further return of profit. With this one, I would like to thank you for the attention for this short educational video, and I see you around in the next one.